talk about something called a radical, which you've really seen before. You might not have heard about it so much in the sense of using the word radical, but when you're doing something like taking the square root of 9 or the square root of 4, you're using radical. Radical is this operator that you see in this picture right here that usually means I'm taking the square root of something. So like if I'm doing radical 4, I'm really taking the square root of it. And I'm saying that, and we know that equals 2. The square root of 9, or radical 9, is equal to 3. So, but up here in this first part, it says the nth root of a number, a, can be written as the radical expression right there. The nth root of a. So, we're not going to touch, nth root means I can kind of plug in any number there and find that number root of some number. We're not going to really talk about them too much past the third roots or the cubic root. But they kind of had the same meaning of a square root. So let's finish filling in this picture and we'll take a look at what we actually mean there. So what that n is, that has a special name. It's called the index. So if I put a 2 there, if I put a 3 there, if I put a 4 there, that's my index. A, the thing underneath that radical sign, is called the radicand, and you're going to hear that word thrown around a little bit. And what's important to note is down here there's this little asterisk that says that if there is no index, so if it's blank, like the ones that I wrote over here, we're assuming that n is equal to 2. That's kind of just assumed in the mathematical world, that I'm taking that if there's nothing there, I'm taking the square root of this number. And so for like those examples that I have with 4 and 9. Okay, so let's scroll down here a little bit. Something that's going to be kind of important here is here. We've got the list of perfect squares. And the reason that's important is because sometimes these problems are going to be really easy if you know what your perfect squares are. So I want you to take a second to write those down. Some of you might already know a bunch of those. And what I mean by perfect square, for those of you that don't know, I'm just taking all our integers and squaring them. And that's the first 12, all the way up to 12. 144 is 12 squared. So that's what I mean by perfect square. The reason that's going to make my life a little bit easier is because, like, down here, for perfect square roots, if you can recognize right away, if you get a problem like this, and you can recognize, oh, I know that 16 is 4 squared, so the square root of 16 is 4, that's going to make your life a lot easier than trying to kind of do the process that we're about to do, which isn't too bad, but your life's just going to be a lot easier if you can do it like this. Things get just a little bit trickier with one like number 3, just because now I've got something hanging out in front of that radical. But what this means right here, this 6 hanging out in front of the radical 289, it's kind of like a 6 hanging out in front of parentheses. I'm implying that I'm taking 6 and I'm multiplying it by whatever is under that radical. So again, if I'm good at kind of memorizing these square roots, you will know, and I know it's not up on our list up there, the square root of 289 is 17. So what this problem is actually saying is 6 times 17, which is 102. And the same goes for numbers 2 and 4. The square root of 121 is actually 11, so this is saying 2 times 11. The square root of 400 is 20, so this is actually saying 3 times 20. So those ones aren't too bad. So let's scroll down a little bit. And this is where things get just a little bit trickier. I actually want you to cross out these 3 steps right here that are in your notes, because I really don't love the way that they are written. And I think it's a fine way and it works, but I think there's a better and a little bit easier way to do it. And what it's called the wedding cake method. And what I'm using this for, the reason I care about it is because notice this says I'm simplifying non-perfect square root. So like a number like 32 or 147, that's not a perfect square root. So I can't just look at it and say, oh, well, I know that the square root of 32 is some number, because I don't know what that is off the top of my head. It's some ugly decimal point. So we're going to kind of break it down and simplify it to make the radical the smallest number that it could be and pull some stuff out from it. So what I mean by that, something that's going to be really important here is prime numbers. And more importantly, a lot of times I want to be looking for the smallest prime number that I can divide into this. So, for example, the smallest prime number that I can divide into 32 is 2. And that's kind of always the one that you want to try to start with. That's your easiest one. So I'm going to divide 2 into 32. It gives me 16. And I'm going to keep repeating this process until I can't anymore. So I can divide 16 by 2 again, and that will give me 8. And then I can divide 8 by 2 again. That'll give me 4. And then by 2 again. And you'll see, this is why it's called the wedding cake, because as I'm going up, it kind of looks like a little cake, layers of cake. And then I'll have 2 again, and then divide by 2 for a final time. And you're going to do it until you get to the birthday candle, or the wedding candle, whatever kind of cake you want this to be. And that's how you know you're done with that process. Now, the way that this works, the reason that helps me is because once you've got all this, you want to start pairing things by 2s. I want to start to pull out pairs of 2. Now I can do it with these 2 right here. And the way this works is for every 2 that I can pair up, I can pull out 1 to be outside the radical. So I've got a 2 I can pull out there times another 2 that I can pull out here. Anything that I can't pull out of the radical is stuck. This 2 is stuck. So what that actually becomes is 4 radical 2. That's my simplified version of the square root of 32. Now let me do a couple of these with you because I know it's kind of confusing. So let's take a look at, let's do 16. Or sorry, 6. So if I start with 180, I can divide that by 2. This gives me 90. Divide it by 2, which gives me 45. Now I can't divide by 2 this time. So what I want to do now is I need to try another prime number. You always want to be trying prime numbers here. So I'll try 3. Just go to the next one. That gives me something. That gives me 15. And look at that. I can pull out another prime number of that. And then the only thing I can divide that by is 5, which will give me 1. My candle at the top. And now I can start pairing off like I did with the first one. Now remember, for every 2, I can pull out 1. So I can pull out 1, 2. I can pull out 1, 3. And my 5 is stuck. So this actually becomes 6 square root of 5. Let's try like number 10, and then I'm going to have you try those other ones on your own. The only thing that makes number 10 look a little bit more complicated is this 2 hanging out in front. But it's really not that much more complicated, Because remember, that just means 2 times whatever the square root of 54 is. All this work that I'm doing up here is just to make this a little bit prettier, to make it not such a big number under that radical. So I'm still doing the exact same process I did in 5 and 6. I'm trying to reduce this, but then in the end, I'm just going to multiply it by 2. So I'm going to kind of ignore the 2 for now. And I'm going to see, can I actually divide this by the smallest prime number I know, 2? I can. It'll give me 27. I can't divide 27 by 2, so let's go up to the next prime number, 3. But that'll give me 9. I can divide that by 3 again. That'll give me 3. I can divide by 3 again, and that'll give me my candle, my 1. Now, you want to look here and figure out what are the things I can actually pair together. The only thing I can pair together are 2 3s. So that's what's coming outside my radical there. And the things that are stuck are this 2 and this 3. So that is what square root of 54 is equal to. But remember, I have to multiply it by 2 now. And the way that works is anything under the radical can only be multiplied by something else under a radical. Kind of like a lot of the stuff that we've been seeing lately, your number math stays the same. If I have a 2 here and I've got a 3 here, I can still multiply those together like I normally would. 6 radical 6. I want you to try 7, 8, and 9. Okay, hopefully you're done with 7, 8, and 9. Let's take a look now over here. Because now we're going to look at perfect cubes. A perfect cube, kind of like a perfect square. Remember, a perfect square meant I was taking a number and multiplying it by itself. Now, a perfect cube, I'm doing the same thing, but instead of multiplying it by itself once, I'm doing it twice. So, like, for example, 1 times 1 times 1, 1 cubed, gives me 1. 2 times 2 times 2 gives me 8. So let me write out those for you, and I want you to copy them down. Because again, it'll make our lives a little bit easier in some cases not. Oops. So then once you got those, let's take a look down here. Notice now, because we said that little number right there, the index, if it's blank, we're just assuming we're taking the square root. But now we got a 3 there, so I know I'm taking the cube root. So I'm looking for a number that I multiply by itself 3 times to get 8. Which if we look up here, remember these all kind of line up with my 1 through, what did we do? 1 through 10. Cube root of 8 is 2. Something that's kind of interesting about a cube root, though, is I can have a negative 1 under that radical. Because if I think about what this means, let me tell you what the answer to this one is. The answer to this is negative 3. The reason that works is because think about what it means. It means if I take negative 3 and multiply by itself 3 times, I'll get the number under there, which for a cube root, that works. Negative 3 times negative 3 is positive 9. times -3 would give me a -27. Okay, let's take a look at these down here. Your process of how you're doing this is really not much different than how we found square roots. Let's look at number 19. I'm going to do my same wedding cake method. And think of the smallest prime number that I can divide that by. Well, it's 2, which is hopefully always going to be, or usually going to be what you can do, because that's easiest. But so when I do that, I get 20. I can divide it by 2 again, and I'll get 10. I can divide it by 2 again, and I'll get 5. I can't divide that by 2. The only thing I can divide it by is 1. And that's going to get, or sorry, I can divide it by 5, and that'll get me my candle. The only thing that's different about these is I have to group by 3s. What I mean by that is if I'm looking at my wedding cake here, instead of trying to get 2 things out from under the radical, I'm trying to get 3. They still come out as 1, but there's only 3. There has to be 3 of them this time. So now this is going to turn into 2 times the cube root. Now I'm stuck under a cube root instead of just a regular square root. 5. Let's look at another one. So if I'm looking at, let's do number 2. $432 I can divide by 2. It will give me, what's that, 216. Divide by 2, that'll give me 108. Divide by 2, that'll give me 54. And now that I'm here, I can't, oh no, I can divide by 2 one more time. Can't divide by 2 anymore, so now I go to my next prime number. 3. 3. Sorry, I'm starting to go into the next. The problem above it. Until I'm left with 1. So now again, I'm doing cube roots, so I'm going to try and group by 3s. One group of 3s there. That 2 can't be grouped in with any other 2s. All these 3s can be grouped together though. So now the things that I've gotten out of the radical, one group of 2s times one group of 3s with a 2 underneath the square root. So that is me reducing the cube root of 432. But what do I got right there? I got a times 2. So I'm going to multiply that whole thing by 2, which is going to give me 12 cube root of 2. Different than the number 21, just because I've got a negative underneath that cube root. Now we can talk about a little bit more why this works in class, but I'm going to have you right from the start. This will only work for a cube root. Pull out that negative. We're going to treat it as if this is -2 times -1 times the cube root of a positive 250. Because I want to get that negative out of that cube root. And what that turns into now is that. And again, we can talk more about why that actually works in class a little bit more, but if you can remember to do that, it's going to make these problems a whole lot easier. And now it looks exactly like number 21 does. So I'm going to start with 250, and I'm going to start my wedding cake. I'm going to start dividing by prime numbers. We can always start with 2 to see if that works. It does in this case. And then once I get there, I have to stop with 2. So now we'll go up to our other prime numbers. Next one up is 3. Doesn't work, so let's try 5. And 5 will work. So if I divide by 5 there, that'll give me 25. Divide by 5 again will give me 5. Divide by 5 one last time, and I'll get my candle. And now everything else just works exactly like number 21 does. I'm going to group by 3s because remember we're doing a cube root. That's going to pull that out in front of the cube root. And then stuck underneath is the 2. So remember, that's just me reducing cube root of 250. Don't forget that we had this 2 out front that we were multiplying by. And the way I'm doing that is I'm just kind of distributing it to that 5 in front. So that's going to give me 10 cube root of 2. So why don't you guys try the rest of them on this page, number 20, 23, and 24.